Hi guys! In our previous lesson, I examined the structure and working principle of operational amplifiers. In this video, we will examine the structure and operating principle of inverting, non-inverting, differential, and integrator operational amplifier circuits. If you have not watched our previous video, I recommend you to watch it first. Now, let's take a look at how the amplification process works with the LM741 operational amplifier, which is widely used in electronic circuits. First, let's look at the inverting amplifier circuit. That is, the value we will amplify is from the inverting input. For example, let Vi be a source with a DC input voltage value. Let's connect this voltage to the inverting input, that is, to input number 2. When connecting, we need to connect it together with an R1 resistor, not directly. We should also connect the negative part of the input to the ground, taking it as a reference point to the non-inverting input. Then we need to connect an RF resistor between input 2 and output 6. Then we need to connect the positive and negative feeds of the operational amplifier. Let's supply positive 12 volts from number 7 and negative 12 volts from number 4. We must also connect the output value between number 6 and the ground, that is, the non-inverting input. So, how do we find the output value? If we show the input value Vi and the output value with VO, VO equals negative Vi times RF over R1. If you ask where we found this, a Kirchhoff voltage law is written at the input and a Kirchhoff voltage law is written between the input and output. Since the currents are equal to each other in these two equations, this equation comes when you replace each other. If you wish, you can look at how it was found later from another source. We can better understand what we are saying by solving an example. Let the input value be 2 volts DC. Let the resistor values be, for example, R1 equals 1 kiloohm and RF equals 4.7 kiloohms. What is the output value? Our formula VO equals negative Vi times RF over R1. If we substitute the values, VO equals negative 2 times 4.7 kiloohms divided by 1 kiloohm. If we do this operation, we find the output value as negative 9.4 volts. In other words, our 2-volt input voltage is increased to 9.4 volts. Since the inverting is from the input, it is inverted to negative value. The output voltage value we will obtain by raising here cannot exceed the positive and negative supply values. In other words, the voltage value we will raise in this example cannot exceed 12 volts. Here, we can think of the negative output as follows. So, if we take a multimeter and measure the output voltage, the voltage value we will see will be negative 9.4 volts. What if the input value is not DC but AC? Again, we will operate by thinking in the same way. For example, let the voltage value of the AC source here be a sine wave AC with a maximum value of 5 volts. Let the resistance values be R1 equals 5.6 kiloohms and RF equals 10 kiloohms. What is the output value? Here we can operate by going through the maximum value. If you wish, you can also find the output value by going through the effective value. Our formula, VO equals negative Vi times RF over R1. If we substitute the values, VO equals negative 5 times 10 kiloohms divided by 5.6 kiloohms. If we do this, we find the output value to be about negative 9 volts. In other words, the AC input with a maximum value of 5 volts sine-shaped AC is amplified to AC with a maximum value of 9 volts at the output. So, what does negative mean here? It means that the input is 180 degrees phase shifted to the output. The graph of the output will look like this. It appears to be 180 degrees out of phase. It is actually symmetrical with respect to the time axis. Now let's look at a non-inverting amplifier circuit. For example, let's again have a source with a DC input voltage value of Vi. Let us connect this voltage to the non-inverting input, that is, input number 3. We should also connect the negative part of the input to the ground, taking it as a reference point, to the inverting input with an R1 resistor. Then we need to connect an RF resistor between input 2 and output 6. Finally, we need to supply positive and negative to the operational amplifier. Let's supply positive 12 volts from number 7 and negative 12 volts from number 4. We can also take the output value between number 6 and the ground, that is, the reference point. So, how do we find the output value? If we show the input value with Vi and the output value with Vo, Vo equals Vi times 1 plus Rf over R1. If you wish, you can look at how it is found later. We can better understand what we are saying by solving an example. Let the input value again be a 2-volt DC input. Resistance values? Let R1 equals 1 kiloohm and Rf equals 4.7 kiloohms. What is the output value? Our formula was Vo equals Vi times 1 plus Rf over R1. If we substitute the values, Vo equals 2 times 1 plus 4.7 kiloohms divided by 1 kiloohm. If we do this operation, we find the output value as 11.4 volts. The 2-volt input voltage has been increased to 11.4 volts. So, if we take a multimeter and measure the output voltage, the voltage value we will see will be positive 11.4 volts. Since it is from the non-inverting input, there is no inversion and the result is a positive value. Here we can see that the output value is higher than the inverting amplifier value. We took the same input values and resistances in both, but the output of the inverting amplifier was 9.4 volts, while the output of the non-inverting amplifier was 11.4 volts. From this, we can see that the gain of the non-inverting amplifier circuit is higher. So how will it be if the input here is AC instead of DC? Again, we will operate by thinking in the same way. For example, let the voltage value of the AC source here be a sine-shaped AC with a maximum value of 4 volts as here. Let the resistance values be R1 equals 5.6 kiloohms and Rf equals 10 kiloohms. What is the output value? Here too, we can operate by going through the maximum value. Our formula is Vo equals Vi times 1 plus Rf over R1. If we substitute the values, Vo equals 4 times 1 plus 10 kiloohms divided by 5.6 kiloohms. If we do this, we find the output value to be approximately 11 volts. In other words, the AC input with a maximum value of 4 volts sinusoidal AC is amplified to AC with a maximum value of 11 volts at the output. Since the input here is from the non-inverting input, there will be no phase shift. It will be the same as the output as it is at the input. This is the working logic of an operational amplifier with inverting and non-inverting inputs. Apart from the inverting and non-inverting operational amplifier circuits mentioned here, many other amplifier circuits are used. For example, the circuit with a capacitor at the input and a resistor between the input and output is a differential operational amplifier circuit. This circuit is used to convert a triangular waveform into a square wave. I will not go into detail about how it works. The circuit created by connecting a resistor at its input and a capacitor between its input and output is an integrator operational amplifier circuit. This circuit is also used to convert the square waveform into a triangular wave. Both of them work with the opposite logic. These amplifier circuits are also used in AC to AC converters. This is the basic structure and working principle of inverting, non-inverting, differential, and integrator operational amplifier circuits. I hope this video was useful and you liked it. Hope to see you in the next lesson. Goodbye!